Hey guys, okay, I want to apologize about the sudden ending of my last video. I didn't manage to get through the May 22. The fire drill went off, so I had to be the consummate professional and go and sort out all of that. So okay, let's continue this. And first thing I'm going to do is I'm going to mark the multiple choice that I'd completed. So let's crack on. I'll present, share screen, entire window for that one. I'll then open this up on my YouTube channel. It's going to blare out sound, folks, very briefly, and then I'll mute it. So that sound's working just fine on that. So I'm just going to then drag that over to my other screen so I can see the chat, that's all. Okay, I'll then set up, so I know the sound's working. I'll then just go to that one because I don't need the video, but I don't get rid of my thing. Okay, let's continue this. Instead, I'm going to mark my other multiple choice, because it was an interesting set of multiple choice. There were a couple of questions which I definitely want to have reviewed. So question 1D to C. It's just nice to check it. I split my screen last time I did this, and I can probably do that. Can't remember how to do it. Sorry about this, folks. It'll take me just a minute to get myself all sorted. Let's go to desktops. And I think I had live streams, May Mark's game. I can then split my screen and mark it next door so it'll just speed up the process. Halve that one as well. All right, let's just check the multiple choice because it was an interesting set of multiple choice questions. I'll get rid of my keyboard. There we go. Okay, so question number 1, I'll do this draw. I'll do it with a green pen. So the first question was D, yeah. Isolated atoms, molecules, all explained. C, 0.56 grams, nice. Question number 3 was B, correct. Question number 4 was B. Question number 5, there you go, chromium 3 chloride, nice one. Number 6 was A. 6B was also A, nice. Number 7, ionization energy was D. Number 8, well, that was a relatively straightforward one, C. Question 9, B, good. Question number 10 is D. Yes, that was one I was concerned about because I wasn't we don't teach that. That is a I've got Farhan. I am done with my A levels. Just wanted to let you know your videos helped me a lot. Thank you, sir. Oh, I'm so glad I could help, Farhan. Anytime, dude. Thank you so much for using my videos and getting such a great grade. So well done. Number 11, C. Nice. B is D. Take it. Number 12 is C. Number 13 and 14. 13 is A. 14 is B. I do not pretend to be flawless, by the way, folks. I will make mistakes. The answer was D. I do not pretend to be flawless. Mistakes are part of being a human being. And what I will honestly say is I thought this one was a really interesting one because you never see half-head arrows in a true mechanism anymore. So nice to see that one appearing. And there's some really lovely learning going on in question 17, recognizing this really neat half-head arrow trick. There's some nice chemistry going on there. This one was an interesting one. I went for the E. Oh, not IUPAC. Cis-trans is not IUPAC. So nice. I like it. IUPAC now swing towards EZ because it's a better version. Cool. I would say that my explanation for that was probably not ideal. Right, let's continue with the long answer now. So I'll try and make everything disappear. Full screen. I like it. The element iron forms 2 chlorides, iron 2 chloride, FeCl293. A known mass of iron powder is added to 200 centimeters cubed of iron 3 chloride. That's interesting. Okay, just draw it out as a picture. I've got 200 centimeters cubed of hot, it's nice to say activation energy being needed there, of iron 3 chloride, FeCl3. And they've given us a concentration as well. That's useful. Moles per dm cubed. When the solution, when the reaction is complete, the solution contains only iron 2 ions. Calculate the unreacted iron is filtered off, dried, and weighed. Okay, the initial mass of the iron is this. The final mass of iron is this. Okay, So it says to calculate the moles of iron that react. So the first thing I need to do is if I've got the initial mass and the final, I need to minus one from the other. So that's the first thing I'm going to do. 6.17 grams minus 3.38 grams. Work out the change in mass. That seems very reasonable. 6.17 minus 3.38. Hello, hi Pursuit. Good to have you back, dude. Thanks for coming. 2.79 grams. That'll be my first mark. Now I need to get it into moles. Number of moles is grams over rams. And I've got my rams of iron is 55.8 off my periodic table. It's always, I've got the number in my head, but I still check it anyway. So 2.79 over 55.8 gives me that. Now that's a really interesting number because what that means is that tells me 0.05 moles. Yeah, there's my final answer. And the reason why that's a good number for me to read, because it's like a white flag. It's saying, oh, that's a good number. If it was a big, long, extensive number, then, it's just when you get nice round numbers like that, it means you're on the right lines. Calculate the moles of iron 3 solution that reacted. Right, now, the thing is they've not given you an equation, so we need to figure out what the equation is. So we've got iron plus iron 3 plus, and it's going to make iron 2 plus. Now we need to balance the equation for this. Now that's really interesting. Some people will just try and balance that straight off the bat. But what I would say is I don't like to do it. I prefer to split this into its half equations and do it that way. It might take a little bit longer, but it's just nice to kind of do this and to show the process. This is going to give away 2 electrons. The iron 3 plus is going to turn into iron 2 plus, and that's going to gain 1 electron on this side. So I need to multiply that by 2. No, sorry, apologies. Multiply this one by 2 to make the electrons cancel. So I now double that, and double that. I now put the 2 equations together. My final equation is going to be Fe plus 2 Fe3 pluses goes to 3 Fe3 pluses, 3 Fe2 pluses. And that should now all balance. I've got 0 from this guy, plus 6 from this guy. That's plus 6. I've got 3 times plus 2, which is also plus 6. The equation balances. Now, that tells me that the ratio between iron and iron 2 is a 1-to-2 ratio. So if I've got 0.05 moles of this guy, then I've got 0.1 moles of that guy. Now, I know this seems completely ridiculous that I'm putting it on my calculator, but I'm still doing it anyway. So that's a times by 2. Neat game. Yeah, that's a nice question. That's got a beautiful understanding in it. If you can do that, then you're doing really good chemistry. Use your answer to AI and AI2 to write the ionic equation for the reaction of iron 2, including state symbols. That's so funny because I needed to do that one to get to my ratio. I thought that's really interesting. Does it tell you the ratio? No, it doesn't. What an interesting thing to do that is, because I've done that one in advance of my moles calculation. I'll circle that, by the way. I don't know why it keeps moving stuff. Every now and again it does this. It decides to, if I just zoom out here, there we go. Right, let's zoom back in. Let's unclick that and zoom back in. So there's my moles. Right, the ionic equation, which I've just given you, and does it want state symbols? Include state symbols. Iron is a solid. We're going to react that with 2 Fe3 pluses, which are aqueous because they're in solution. And I'm going to form 3 Fe3 pluses also in Fe2 pluses, sorry, also in solution. And it says you must show your working. So the working out, of course, is this bit. Really interesting. It's nice to do that. Fe going to Fe. By the way, for those students who would be tempted not to include this then, because it's up above, you must do it. I have to move this down. I'm just going to write out the equation I've done above, but it is just nice to be able to actually show the working out and the fact that this is going to cancel with this. So it's nice for me to show the 2 half equations, the overall equation at the end point. Nice question, though. Really like that. Next, the concentration of the solution obtained in A is increased by heating it gently to remove some of the water. Okay, I had 200 centimeters cubed of it before. Yeah, I'm going to remove some of it. Yeah, so I've got started off with 200. Yeah, and the Fe 2 plus, we can even work out the total number of Fe2 plus I'm going to create, because this is in a 1 to 3, right? That's in a 1 to 3. Not that I think I'm going to need it. 0.15 moles of that guy in 200 centimeters cubed. Okay. It then says calculate the number of moles of water. Oh, okay. Heating it gently removes solid, pale green, solid crystals contain. Okay. This question actually, one of my students came and asked me about not so long ago, so it rings a bell. And it's nice just to talk through the process of this. We've got FeCl2.xH2O. And they have told me that this contains 28.1 grams, percent iron. Yeah, now this is a clever trick, this, because what you now need to do is you now need to make a really big assumption. In order to work out the moles of crystallization, you need to be able to get mass of it. So what you're going to do is you're going to make a massive assumption that you've got 100 grams of FeCl2.xH2O. Yeah, because what that means is we can then say that we have got FeCl2.xH2Os, that if you've got 100 grams of this, yeah, then what you realize is that you've got 28.1 grams of that. That's what we can do by making the assumption. Now, at that point, we've got grams. We can get to moles of just iron. So iron weighs 55.8. Let's get to the moles of it. 28.1 divided by 55.8. Now, remember, in chemistry, one of the most important tips I can ever give you is get to moles. Because if you can get to moles, then the whole point of a mole is to count particles. So I now know the number of particles of iron I've got. Now, the cool thing, the next assumption that we make is, not an assumption, the formula tells you, in this whole structure, there is one iron. So if there is one iron, we have one whole molecule. The ratio in terms of iron to the whole molecule is a 1-to-1. Yeah, because one iron is in one of these entire things. What that means is that the moles are the same. We've also now know that we had 100 grams of the whole solid. So what I can now do is I can do number of moles is grams over, I shouldn't be doing it in green. Number of moles is grams over rams, and I can reorganize for rams. Bring the rams over, bring the rams over, bring the moles down. So this is rams equals grams. You notice that every time I do a question, I reorganize. I never just quote a reorganization. I have learned one equation, and I've learned to reorganize it. I've got 100 grams of the whole molecule, and I have 0.504 moles of it. This is because the moles of iron is equal to the whole moles of the molecule. So 100 divided by 0.504 gives me an MR of 198.4. Now, I'm just going to tell you that I've picked up a rounding error here because this number here was a nightmare. I should have gone to 5 decimal places. Or 5 significant figures, because if I do 5 significant figures, then I'm guaranteed not to get a rounding error. Yeah. So what I can now do, now that I've got a rough MR, I'm only looking for the value of X anyway. So what I can now do is I can subtract all the people I need to. Minus 55.8, that's the AR of iron. Minus 35.5 times 2, the 2 chlorines. This is Fe. This is Cl2, which is here, by the way. Yeah. After I've taken those away, I'm only going to have water left. So minus 55.8 equals minus 35.5 times 2, and I get a value of 71.6. Now, this is only waters. So what I can now do is I can do 71.6 over 18.0, the MR of water, over 18, and I get a number of 3.98. So my X equals 4, and you never delete that real number, and I'm done. What a great question. Gotta love it. There is another method to do, but I'll just leave it at that one for today. Okay, naturally occurring bromine has 2 isotopes, bromine 79 and 81. State what is meant by the term isotopes. Atoms, plural, with the same, I'm just going to turn my microphone around a bit. Atoms with the same number, shouldn't shortcut it, Mr. Duncan, don't do it. Same number of protons and electrons. Now, I know in the mark scheme it'll probably say ignore the electrons. I just like to do it. Yeah, same number of protons and electrons but a different, notice I go into a different bullet point, by the way, but a different number of neutrons. Now, I'm just making you aware, different number of neutrons, just to make you aware. They've given me a context, yeah? They've given me bromine 79 and 81, which means I really ought to show them my calculation here. There's no point because they're asking me to do it in the next one anyway, yeah? So, but usually what I would do is I would actually write down bromine is bottom number is 35, so atomic number 35, and they've given me 79, and then I've got bromine 35 and 81, and I would just work out the maths of this. So I'm going to do protons is 35 for both, electrons is 35 for both. Notice the similarity from the previous paper, by the way, that I did. There's no charge on any of these, so sometimes they add a charge to throw the electron number off. Yeah, but the neutrons are going to be different. So I'm going to do 79 minus 35, and I get 44. And then I get 81 minus 35, and I get 46. Now, for those students who would probably go, oh, you don't need to do that last one because you can just use the previous number and know that that's too higher. I totally get it. I actually ran it through my calculator because it doesn't just give me the answer, but it also proof check my last one that I've not made a silly mistake. Just so you know. The mass spectrum of the sample of bromine is obtained. Draw a dot and cross diagram showing the bonding in a molecule of bromine, outer electrons only. This is the easiest dot and cross question that I've seen in a long time. I'm really shocked at how basic this is. Like usually there are some really tricky dot and cross diagrams these days. If you've not seen them, then you've not done enough practice. Some of them are really tricky. Yep, nice and easy. One of them is dots, one of them is crosses. Next, describe the formation of the molecular ion in the bromine in the mass spectrum. Include an equation. Cool. Okay, describe the formation of the molecular ion. Electrons, high energy electrons from electron gun, knock off outer electron from bromine molecule, Br2 molecule. Include an equation, Br2, and it's the formation of it, plus an electron goes to Br2 dot plus. It's actually a plus dot, by the way. That comes in terms of fragmentation. I'm going to add the dot anyway, just because I like to do it. Plus 2 electrons. Don't forget that they must be in gas. We know that bromine is one of the 2 elements, well, some of the elements here on the periodic table you need to know, and bromine is one of them. There are 2 liquids on the periodic table, bromine and magnesium, bromine and mercury, the only 2 liquids. What that means is they like to use it for things like mass spec because people will tend to put it in as a liquid. Just watch out. You can't remove an electron from something that's not a gas. That's a rule, by the way, because otherwise the energy of the electron will go into breaking the bonds between the molecules, not the electrostatic between the electrons and the nucleus. So just bear that in mind. Okay, on the mass spectrum grid, draw the peak for the bromine molecular ion, showing their relative peaks. So, okay, we know that bromine, it's giving me a little bit of space down here. We know that we could have Br79 bonded to Br79. We've got Br79 could be bonded to Br81. And we've got Br81 bonded to Br81. So we can work out their numbers immediately. 79 plus 79 gives me, I'm going to have a peak at 158. And then I'm going to add 2 to it, but I'm going to do the math anyway because it's a confirmation of my previous one, 160. As I said, it's more of a proofing than anything else. 81 plus 81 gives me 162. So I know where they're going to be now. Yeah, 158, 160, and 162. Now the ratios are a bit more tricky. So the ratio trick that I'm going to teach you now is a Punnett square trick stolen from biology. And you can use this for the diatomic elements. You can't use this for anything that has, I'll mention the 3, the times when you get 3 in it. But with the diatomics, you can do this because you've got 2 versions of it. Bromine 79 and bromine 81. And this is in a 50-50 ratio, otherwise known as a 1-to-1. So I can put 1 here and 1 here. If this is also a Br79, 1 ratio to Br81. Yep. So it's a 1-to-1 ratio, and then I can work out the numbers. This is going to be 158, 160, 160, 160, 162. So the ratio is going to be a 1 to 2 to 1. So relative abundance, I don't think they really care the numbers that you pick as long as it's double. So I'm going to take that one to 30. The 60, the 160, I'm going to take to 60, double the height. And then the other one, it won't matter which numbers you pick. You could have done 2 and 4. You could have done 4 and 8. They didn't really matter. The relative abundances is up to 100, so it's not a percentage, so you don't worry about it. Yeah, I'm just going to show you this for the chlorine, by the way. Just since we're there, we know that chlorine exists as chlorine 35 and chlorine 37. And we know this is in a 3 to 1 ratio. So if I was going to do my Punnett square for the molecular ion peaks, I'm going to do 35, 35, 35, and 37. There's the 3 to 1 ratio. Yeah, there's the 3 to 1. Do it the same for the other isotope. Sorry, the other atom in the molecule of Cl2. Same 3 to 1. Yeah, what I can now do is work out the numbers. So I'm going to get 70, 70, 70, 72, 70, 70, 70, 72, 70, 70, 70, 72, 72, 72, 72, and 74. This is in a 9 to 6 to 1 ratio. I know that most of you will be looking at this going, I've already remembered those numbers, 9, 6, 1. I've got it in my head. That's great if you do, really useful. But what happens if they throw you something you've not seen before? What happens if they throw you fluorine? Fluorine exists as 19 and fluorine 18, and they tell you it's in a 2 to 1. They could ask you, they could give, this is something that they can do. So what I'm going to do is I'm going to go 19 twice and 18 once, 19 twice and 18 once. And I'll run the numbers together. 19 plus 19 is 38. 38, 38. This is going to be one less, 37. I'll check that. 19 plus 18. I always check these things. 38, 38, 37, 37, 37. And then you're going to have a weird 18 plus 18, 36. 18 plus, calculator, 18 plus 18. Yeah, 36. And I'm going to get a 4 to 4 to 1. Yeah, so it's just nice to show you how this game plays out. Okay, next one. The percentage abundances of the isotopes in the different samples of bromine are shown. Calculate, do I need to do anything else? No. Calculate the molecular mass of the bromine sample, giving the answers to 2 decimal places. Oh, okay. Give the relative molecular mass of the sample of bromine. Molecular. Interesting. It's not asking me for the relative. It's not asking me for the relative atomic mass, but relative molecular mass. Oh, you're working out the average anyway. Lol, because it's RAM, isn't it? Okay, that's really neat, by the way. So I'm going to work out the AR, the relative atomic mass. And I do that by doing 79 multiplied by its percentage, 56.38. Yep, I'm going to add that to 81 multiplied by 43.62. God, that stumped me for a little bit, all over the total percentage because this is in a percentage. If this was a ratio, and not an abundance, they could give us any number they like. Yeah, this is the ratio of 6 to 2. And then I'd be dividing this by the sum of the ratios. Just reminding you of that fact, folks. They're very common questions. Right, let's run it through to get the AR. 79 multiplied by 56.38 equals, plus brackets, 81 multiplied by 43.62, close brackets, divided by 100. And I should get a number in between these two, but closer to 79 than to 81, because that has a higher abundance. And I do. I've got a relative atomic mass of 79.87. Now, this is a bromine atom, Br. And we know that Br travels around in pairs. So I'm going to take that number, I'm going to multiply it. That's a neat trick. Br2 is 159.7. Gotta love it. Really like that question. That's really neat. Haven't seen one of those before. That's a sneaky trick. The element carbon and silicon both form dioxides. Carbon dioxide is a simple covalent molecule, but silicon dioxide is giant covalent. Describe the covalent bond between a silicon atom and an oxygen atom in silicon dioxide in terms. So we're comparing them. No, hang on. Describe the covalent bond between a silicon atom and an oxygen atom in silicon dioxide in terms of the particles involved. Okay, so your silicon oxygen bond in silicon dioxide is a standard covalent bond. Yeah, covalent bond where one electron has come from each atom in the bond. I'll draw a picture. I'm going to go like this: silicon, oxygen, dot and cross. It is a standard covalent bond. Yeah, one electron has come from each atom in the bond. That's an interesting 2 marks. Really curious to see what the second mark's going to be from that. I wonder whether or not they wanted me to say it in bullet points as silicon brings one electron, the oxygen brings another electron. Yeah, I can do, but it's nice me to just, I can guarantee myself for the picture, X comes from oxygen. I won't do that. They wouldn't allow that. They'd say there was a dot there. O comes from silicon. By the way, I love chemistry because in reality, we know that the diagrams can get you marks. It's one of the lovely things in terms of chemistry compared to the other sciences. Compare and contrast the covalent bonding in carbon dioxide and silicon in terms of orbital overlap. Okay, so carbon dioxide, CO2 is C double bond O on either side. But in reality, what we know in reality is happening, and I'm going to draw this. We've got sigma overlaps. These are head-on overlaps. It's gross, this. Yeah, so this is a sigma bond in terms of overlaps, but it also has a p overlap. That's not very good. I can do that better. A p overlap with this one. Oh, go back. Evil thing. There we go. And a p overlap with him. And then this one has p overlap. I don't like the way it does. My laptop does this. It's really weird. I actually can do that better as well. And then this one is like that. That's not that. There we go. Oh, undo. Stupid laptop. So we've got, and these are pi bonds. I'm drawing the pictures of them. Pi. Yep. So carbon dioxide, CO2, has sigma bonds and pi bonds. Sigma head-on overlap of orbitals. Pi bond sideways overlap of p orbitals. SiO2 only has sigma bonds, only head-on overlap of orbitals. Love it. Interesting question. Kind of like it. Can't wait to see the mark scheme for that. Dead nice. Next, the shape of carbon dioxide molecule affects its physical properties. Explain the shape of the carbon dioxide molecule. Okay, so first of all, bullet point number 1, straight off the bat, is you should know that it's linear. Yeah, that is there are 2 examples of linear that you need to know, and the 2 examples are carbon dioxide being linear and beryllium dichloride being linear. Yeah, those are your 2 examples of linear. Yeah, and explain the shape of carbon. Now, there are no lone pairs around the central atom of carbon. Yeah, so we're going to say carbon forms, explain the shape, forms 2 double bonds. This is a horrible question, by the way. 2 double bonds. No lone pairs. No lone pairs on the carbon. Electrons in double bonds, repel to be as far apart far apart as possible, minimizing repulsion. Minimizing repulsion. Cool. Interesting question. Really interesting shape one. Explain the polarity of the carbon-oxygen bond. Okay, so the first thing I'm going to tell them is that the carbon-oxygen bond is polar, and I'm going to draw the diagram as well. So I'm going to say that this is delta positive and this is delta negative. Yeah, so is polar, and I can put it is polar. Carbon is slightly positive. I don't really need to, by the way. Oxygen slightly negative. Don't really need to. The diagram would have got me the mark slightly. Come on, Mr. Duncan. Now I need to tell them why. Oxygen has a higher electronegativity. You tell them why. Electronegativity than carbon. So electrons in bonds are closer to oxygen atom. Full stop. Can't wait to see the mark scheme. It's a great, I'm loving the questions. Looking forward to seeing the mark scheme though. Feel like it's going to be good reinforcement of these kind of skills. It's really nice. State whether or not the carbon dioxide molecule is polar. The bond is polar. Yeah, that's a good point. Is polar, bond is polar, because the molecule itself is non-polar. Yes, the answer is state whether or not it's no, not polar. Symmetrical molecule, polarity cancels out. Now, I don't really like that as an answer, by the way. It's not very good chemistry, is it? Cancels out. But what I want to say, so an even, because the definition of polar is an uneven distribution of electrons, which we have in the C double bond O's. But when they're symmetrical, there is an even electron distribution. I'll show you the picture. Electron distribution. I don't know why I'm singing, guys. Sorry about this. So if we look at the carbon dioxide molecule, the electron cloud, although it is it cancels out. It's symmetrical. That's an equal. There's no end which is more positive or negative than each other, because it will cancel out. Even distribution. Neat question. Use your knowledge of the structure and bonding to suggest how the structure of silicon dioxide is similar to diamond. Oh, I like it. The atoms are silicon atom, Si atom. I should be doing this in red, really, shouldn't I? How the structure is similar. Both giant covalent. Structures, or macromolecular giant covalent structures. Shape, this is the thing I'm going to probably get, by the way. Shape around silicon and carbon atoms is both tetrahedral. Tetrahedral. Bond angle, 109.5 bond angle. Same thing. Love it. Seems reasonable to me. It's only one mark. Don't want to waffle too much. Give a possible reason why silicon dioxide has a lower melting temperature than diamond, even though, the bond is polar. Give a possible, even though the silicon oxygen bond is stronger than a CC. Oh, that is mean. First question, can we say three-dimensional? I'm going to say that it's not enough, Pursuit. It's a bit too vague. I wouldn't like, yeah, they are three-dimensional, but You could be different three-dimensionally. You're commenting on the shape and things like the bond angles that you know are going to be exactly the same. Your answer would be too vague. Be careful. Yeah. This is guys, can I just say, of all the questions so far, this is the first one that's really intrigued me. So I've gone and moved something. Really moved it too. Stupid laptop. It's doing silly things. Still moved it. Move it back. Come on. There we go. I'm back. Okay. So the answer is going to be that these silicon oxygen bonds are polar. You could say I can't wait to see the mark scheme for that. Look at how many lines there is. Give a possible reason. Silicon oxygen bonds are polar. Now, the thing is, you see, they're telling you that it's stronger. Melting point means that less energy is needed to break the bonds. Well, it's interesting that they're saying that the bonds are stronger. Therefore, I mean, I can tell you that there's one fact is going to be that the SI bonds are polar. I'd be hilarious if that was a simple scheme. I'm also going to say that oxygen atoms have lone pairs. Yep, have lone pairs on them. Two, in fact, brackets, two lone pairs. Yeah. This would add repulsion. Yeah. It would add electron-electron repulsion. It will add more repulsion. More repulsion to the structure. Within the structure, more repulsion within the structure. Weakening bonds. How fascinating. Can't wait to see the mark scheme for that one. That has intrigued me. Deduce the molecular formula for, ooh, gross. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. C15. Count the number of double. We did this last time. They gave us a similar trick on the last paper. 3 double bonds. We know if it was an alkane. By the way, there's another trap. There's also a cyclo in here too. That means I'm going to have to... that's a trick, folks. If you have a double bond or a cyclo, take away 2. So this means I'm actually going to... So usually I'd double it and add 2. That would be 32. But I'm now going to subtract 2, 4, 6, and 8 for the cyclo. So minus 8. 32 minus 8. Calculator on, please. Minus 8 gives me 24. So I'm going to do this. Now, I know that I don't want to waste time here, but it's nice for me to kind of confirm my concept here for you. So if we just, it's nice just to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Nailed it. That seems very reasonable to me. Again, looking forward to seeing the mark scheme. Name the type of mechanism shown below. Oh, it's electrophilic addition. So we've got electrophilic. If anybody's named the type and mechanism for the reaction, that's really interesting because the mechanism is addition. The type is electrophilic. But I'm just going to put in electrophilic addition, as you always would. That's your 2 marks. Gotta love it. Oh, but only 1 mark in the type and mechanism. That's so annoying. Should be worth 2 if they're going to ask you 2 questions. Yeah. Next. The diagram shows a similar structure to zingiberine, in which part of the molecule is represented by A. Complete the mechanism with 1 molecule of HBr, include curly arrows, lone pairs, etc. Cool. So we're going to go, I'm going to add HBr in here. Don't forget, stage 1 in any mechanism is find your polarity. Double bond reaches out. Notice how I'm literally touching the middle of that double bond. Sir, you missed part A. Did I miss a question? Did I? Oh, stupid laptop. It's doing weird. I think it's because my mouse might be a little bit too close. I'll go back up. Thank you so much, Pursuit. Did I miss a question? Miss part A. On the structure, draw a circle around the 2-methyl group referred to in the name. Thank you very much. Okay, so 2-methyl. Longest thing is going to be, let's just highlight this just to show you what the longest chain is. Yeah. And then you've got this, that's a branch, and this is 2-methyl. Ooh, 2-methyls, because look, diene, look at the diene here, folks. Cyclohexane. So hang on a minute. If that's going to, look at this, this is a branch. That's the way we need to break this down. This is a really good question. I'm so glad. Thank you so much, Pursuit. 1 house point. Well done. Okay, let me color code this. So we've got, always go to your main stem. Cyclohexane 1,3,5-diene. Let's just highlight this guy there. Okay, and we can see the diene. Let's now highlight the branches. So we can now go to, this here is this is weird, isn't it? 2-methyl 5, 6-methyl het 2-yle. This is a branch. This is a big, long branch. This one here. Yeah, that's that one there. And then you've got branches on branches, which is hilarious. Well done, EdXL. I like this question. A 2-methyl on the branch. And this is 6-methyl heptane. 6-hept-2-ene 2-yle. Blimey, that's the carbon number 2 here. That number 2 there is there. Yeah, because it's a 2-yle, so carbon number 2 off the cyclo. Yeah. 5-ene, that makes sense. 1. My laptop's done something weird. Uh-oh, it's frozen. Uh-oh. It'll come back. No, that just cut me off. Something weird. Stop. I don't know why this thing, maybe my laptop's going on to. Oh, right. Sorry, guys. My laptop was not on charged. I'm really hoping I'm still streaming live. I think I am. Still going. Thank goodness for that. My laptop went on to power saving mode. Okay. Sorry about that, folks. Okay. This is a really interesting question for 1 minute. Really nice. So this is number 1. This is number 2. And then 3, 4, 5, 6, 7. So the question then is, where's the 2-methyl heptile? That's your 7. Hept-5-ene makes sense. Yeah, the 2-yle because it's on carbon number 2. And then there's a 2-methyl. Cyclohexa. So hang on a minute. No, because this is going to be the diene. You've got to count over and above it. 2-methyl 5, because this is going to be atom number 5 here. Look, this is atom number 5. Because it's telling it where it is on the cyclo, right? That's where it is on the cyclo, which means we've got to count over it. So 1, 2, 3, 4, 5. The methyl's there. Okay. Oh, that was not nice. Didn't enjoy that. Yeah. So let's find out where the other methyls are then, because that's really interesting. This is the other methyl one, and that methyl is the 6-methyl there. So the answer is this guy. Neat question. Thanks, Pursuit. What does dimer mean? Dimer? Looks like a dimer. A diene. Oh, diene. Yes. A diene means that there's 2 enes. Yeah. If you do, we know that this here is propene. Yeah. All the H's go on, the correct number of them. There's propene. Yeah. But if I add another, you don't need to do dienes, but it just shows the fact that you don't need to be able to name them, but you need to be able to use them. Yeah. If I add another double bond in this, just like you've learned in all the other naming, yeah, this is going to be a diene, 2 double bonds. This is buta with the A. It's a weird one, year 13. Buta 1,3-diene, meaning 2 enes, and it's on carbon number 1 and 3. That's how you get it. Hope that helps. Great question, Pursuit. Thank you. Right, back to my mechanism. So easy to miss a question. I would have done it. Would have missed it. Thanks, Pursuit. Right, now that I've done that, I need to make sure that I break my bond going in the opposite direction. The arrows move away from each other. Right, product of this. So I'm now going to break this bond. double bond broken. Now, what am I going to form here? I'm either forming a tertiary. Does it tell me which one it wants me to do? HBr. I'll tell you that the H goes onto the carbon with the most H's already. So I'm going to put the H. The carbon positive will go here. Let's just check the molecule and where the Br goes. Yep, that's totally fine. Yep, so that positive goes there. By the way, if you're wondering what I did there, sorry. What I did was I spotted this section, which is what they're showing me, and I saw that the bromine is attaching to that carbon, not this one. So I know that my H is going there. So the H has just been attached on, by the way. So my H is here, just so you know. And then the Br minus, circle your charge, add on your lone pair. That's now going to hop on. And the reason for this is because this is a tertiary carbocation. Gotta love it. Tertiary carbocation. Carbocation. It's by the Red Hot Chili Peppers. Product. It doesn't matter that I've shown it going down. They drew it doing this. That's totally fine. It's the same thing. It's totally the same thing. Next, for this reaction, there are two possible products. Yes, there are. Explain why one is the major referring to your mechanism. Yeah, figured. Yeah. I is major since it goes via a tertiary carbocation. Two goes via a secondary carbocation. Secondary carbocation. Carbocation. Tertiary carbocation, more stable. Due to the positive inductive effect. Now, you don't really ever need to mention this, and I don't think you're going to need it. I think you're going to get it for stable on its own, positive inductive effect. But it's good for you guys to hear me using this term. Go to the next one. Really looking forward to getting to the mark scheme of this. How many questions to go? It's a lot. We're nearly there. Cool. Next, identify the catalyst by name or formula. Nickel. Hydrogenation. I'm adding hydrogen. 1, 2, 3 of them to boot. Nickel catalyst, 60 degrees, hydrogen gas. Next, 2 moles of zingiberine react completely with hydrogen at 150 Celsius. Oh, I need to go higher in my temperature these days. I did notice that on a mark scheme. It was a subtle change. Didn't tell me. And a pressure of 120 kilopascals. Calculate the minimum volume of hydrogen needed under these conditions, stating the units. Okay, so 2 molecules react completely with hydrogen and the pressure of this. Calculate the minimum volume of hydrogen needed under these reactions. 2 moles react completely with hydrogen. Okay, that's weird. So if 2 moles of zinc, I know reacts in a 1-to-3 ratio. One of these reacts with 3 of those to destroy all the double bonds. So 2 of them would react with 6. That's a trick. Blimey. Don't like it. I could have got most of the marks even without doing that, by the way, because what I can do is I can now go PV equals nRT. Remember, this is not a mark, but because they've given it to you, but there's a mark for the rearrangement. We want the minimum volume. So I'm going to rearrange this and get rid of that. There's my first mark in the exam. Nice. Now, the moles is the tricky bit, because I think lots of people might just lob in number 2. You can still get 3 marks out of the 4 if you don't use the ratio, but it's going to be 6. So N equals 6 for hydrogen. The R is 8.31. They tell us this. The temperature, they gave us it in Celsius. I need to add 273. So 150 plus 273 equals, this is another mark, doing the conversions. Don't forget to do your conversions. 423 Kelvin. My pressure, they've given it to me in kilopascals. I can't do that. I have to be in pascals. 120 times by 1,000. gives me 120,000 pascals. And this is going to spit me out in meters cubed. Yeah? Let's lob in all my numbers. So I've got 6 multiplied by 8.31 multiplied 423 all over a pressure of 120,000. And I'm going to get a volume in meters cubed of 8.31 multiplied by 6 multiplied by 423. Careful, Mr. Duncan, type it in properly. Divided by 120,000. And this will spit it out in meters cubed. 0.176 meters cubed. I wonder how big that is. Oh, that's 107. That's 107. That's a lot. 176 liters? Wow, that's a big volume. Ouch. I'm going to check my calculator. It's a lot of gas, that. 6 times 8.31 times 423. Okay, divided by 120,000 gives me the same number. Okay, cool. That's all I can do is to check for these. This is a hard thing to catch, those kind of mistakes, if you make them. Name the process that forms these gases in landfill. Decomposition. Organic waste may be disposed of in a landfill. Both processes include produce gas. They produce percentage typical in landfill. Name the process that forms these gases in landfill. It's biodegrading because it's organisms eating it. That's why you get methane. Decomposition or biodecomposition, biodegrading. I don't like the word biodegrading. Oh, I don't like it. Biodecomposition. Gross. Degrabbing. Nice one, Mr. Duncan. Biodegrading. Decomposition. Stroke decomposition. Decomposition. Don't like it. Organic breakdown. State the main environmental, I can't wait to see the mark scheme for that one. State the main environmental problem caused by landfill gases. Identify the gas or gases responsible. The main environmental problem. Well, in the heck. Global warming, stroke climate change. I never do those separate now. I just automatically put them together. Climate change. Explain why. CO2 and CH4 are greenhouse gases. Love it. Seems reasonable. Next, 1 ton of landfill waste produces approximately 12.5 dm cubed of landfill gases per day. Calculate the mass of carbon dioxide produced in a year by a typical landfill site. Oh my goodness. Which contains 90,000 tons of waste. Assume that the gas is measured at room temperature and pressure. Gross. Okay, fine. So 1 ton. Ugh. Come on, Mr. Duncan, speed up a bit here. 1 ton equals 12.5 dm cubed of gases. So 90,000 tons. 90,000 tons is going to be 12.5 times 90,000. Just count my zeros. Gives me 1, 1, 2, 5, 1, 2, 3 dm cubed. Be nice for me to convert to meters cubed, but meh, why bother? I can do. I can divide by 1,000 and put it into meters cubed if I want to. Or 1,125 meters cubed. I just like doing that. Yep. Now the problem is, you see, that's not over. Because what we now need to realize, they're asking us for carbon dioxide, and it's got a percentage. So it's 45%. Perfect. So I'm just going to divide this by 100 and then times it by 45. Check my percentage again that I've got the right one. Yep, carbon dioxide. I like it. So I'm going to do that divided by 100 times by 45. And I'm going to make a volume of 506.3 meters cubed. Gross. Oh, and this was in a day. Per day. So close. Meters cubed per day. You see, Mr. Duncan, RTFQ, just read them through. Be careful. And this says per year times 365 times 365 gives me, holy guacamole, 1,847,81 meters cubed. Gotta love it. I'm glad I switched to meters cubed now. I was going to get a redonkulous number. Can't wait to see the mark scheme. Suggest two advantages of incineration over landfill. Okay, landfill is all about space. Less space needed. Top advantage. Less space needed compared to landfill. Second top one. Incineration can be used to generate electricity. Top answers. Boom. Environmental groups prefer recycling to both landfill and incineration. Suggest one advantage of recycling. One advantage? No toxic gases. That's interesting, that. Environmental preferred recycling to both landfill and incineration. One advantage. Recycling. Nothing's going to landfill. No toxic gases from incineration. Produced. Fine. Done. I think I'm finished with the paper, right? Maybe? Have I got a part C? Always go to the end of the paper. I'm done. Right. Let's run through the mark scheme for this section. At least I've managed to complete the paper. Cool. Let's have a look, folks. Right. I've already got the mark scheme there. I just need to split my screen again. Let's split my screen. Let's make that go to full screen like that. Okay. Cool. So in green pen, I've got 2.79 over 55.8, and I've got my 0.05 moles. Love it. Next, 0.1 due to my ratio. Love it. Yep. Next, expression. Oh, that's neat. They wanted an expression from this. Is it expression for concentration and substituted values? Correct answer with some working scores too. Okay, so I do have the correct one. I just used the method that I did to create it. So I'm so glad I didn't remove any of my working, because it makes totally reasonable sense, right? But that's an interesting one. They wanted me to substitute the values. Concentration equals moles over volume. Yeah, and they wanted you to get to the moles 500 times by 200 over 1,000. Fair enough. Interesting. Huh. Anyway, interesting. It's not how I would have done it. Next, calculate the whole number ratio, given the ionic equation. All state symbols are provided. So there are my state symbols. Correct ratio is given. You can see that over there on the right. And I can calculate the whole number ratio. Yeah, fine. Standalone, kind of no working, max 2. I split it into its 2. Allow multiples. Correct species in the reaction. It's interesting that. Use your answer to write the ionic equation. Yeah, okay. I'm not entirely sure I've shown that very well. I probably wanted to highlight these as my moles. That's interesting that. I've definitely got 2, but I mean, I'd probably get 3 in reality, but it's nice to add on that. I should be showing some kind of numbers and comparisons of the mole ratio, maybe, but I feel like this gets me the mark anyway, but it's an interesting question. Not the one I'm really fussed about, but still. X is 4. It's nice to see that over there immediately. 198.4. I got a rounding error. Picked up a rounding error. What's it say about that? Ignore significant figures. So the rounding error will be okay, but it's just a case of not particularly great. I'd still want a mental no, 5 sig fig. If you're worried about, if you're doing long calculations, guys, and you're worried that you're going to pick up a rounding error, if you do 5 sig fig, you will never get a rounding error. I spoke to a maths teacher about it. So anyway, you kind of get the premise. I've worked out the MR down here. Yeah, I did RFM minus all my numbers, 126, and then 71. There's my 71.6. I've got 71.7 or 71.6. Yeah, so they actually do the same. Oh, by the way, there's going to be another method, isn't there? Alternative method. There are alternative methods to this. Alternative, there it is. Yeah. So you can have a look through that if you like. But anyway, it works out well. And there's the 9-8 as well, which is nice. Next, atoms with same atomic number, different mass numbers, except proton number and same number of protons, different number of neutrons. That's fine. Yep. And then it wanted, there's a calculation even being shown on the additional guidance, which is kind of nice. Yeah, then the next question wants us to fill in these numbers. So, go away. So we've got 35s, 44 and 46 and 35. Nice. Next, my good old bromine. That was like the easiest dot and cross ever. Loved it. Next. High energy beam of high energy electrons striking the gaseous bromine molecule. Equation for the formation. Allow high speed electrons. Allow electron gun. Amazing. Yeah, molecular ion. Do they allow the dot? Don't really need it. Ignore state symbols. I won't include the dot next time because it probably confused the AS marker. Grid, they did 40 and 80, but it's any ratios. There's the correct numbers. Yeah, you can see the numbers down there. The ratios in a 1 to 2 to 1. Like it. All good so far. I loved this question. Thought it was really, really clever. Really neat that. 2dp. Calculate the relative. Oh, I lost it. Damn, Mr. Duncan. I lost a mark. I do not pretend to be flawless. 2 decimal places. Lost it. Throw it away, Mr. Duncan. Throw it away. But the rest of it, I'll do get the other 2. But easy done. I do not pretend to be perfect. Next, this one I found really interesting. Yeah. Both molecules contain sigma bonds, covalent bonds where one has come from each of the atoms. Have I missed a question? No, I haven't. Have I skipped on a mark scheme? Yes, I have. Strong attraction. So it then says, describe the covalent bond between terms. I've schoolboyed errored it. Okay, there you go. Ignore reference, allow, place protons. Yep. Guys, totally missed that question. Totally missed it. Yeah, that's an issue. Yeah, it's saying describe the covalent bond in terms of particles. Totally missed it. Yeah, I'll take the feedback. Yeah, the electrostatic attraction. Made a mistake. I do not pretend to be perfect. If you've got a problem with it, don't watch these videos. The electrostatic attraction between the shared pair of electrons and the 2 nuclei. Shared pair of electrons and the silicon and oxygen nuclei. Easy mistake. 0 marks. Lose it, Mr. Duncan. Went too simple. It happens. Part of life. You'll have to forgive me, folks. As I said, I do not pretend to be perfect. I just do these because I think some people find it useful. Okay, both molecules have sigma. CO2 has sigma and pi, has sigma only. Description of end-to-end overlap. Carbon dioxide, sideways overlap, pi bonds. I will take all 3 of those, though. Thank you very much. Next, linear. So there are 2 sets of bonding electrons, no lone pairs like it, with arrangement to minimize repulsion. Got that down there. Yeah, shape is linear, given a bond angle of 180. Bonding, like no lone pairs, 2 double bonds. Yeah, I'd give myself that one, but maybe want to add more detail in the next time. Mention the bonding pairs. Next one. Carbon atom is slightly positive and oxygen is slightly negative. Love it. Except shown on a diagram. Perfect. Because oxygen is more electronegative than carbon. Next. It is non-polar because it's linear and dipoles cancels. Allow symmetrical molecule. Polarity cancels. Polar bonds cancel. Charges cancel. I'll take it. Cool. Next. Shape-wise, tetrahedral. Love it. It's only 1 mark. I'll take it. These are polar. Please say it is. There are fewer bonds per atom in the structure. Fascinating. Okay. Allow reverse argument. Allow oxygen only forms 2 bonds. Allow bond strength as an average. Allow oxygen has lone pairs of electrons. Yay! Ignore silicon-oxygen bond is polar. Ignore reference to signs of atoms. Phew! Ignore. That's right. Yeah, because it doesn't really like that. The polar bond will mean it'll be attacked. It doesn't really weaken the bond so much. So in reality, the lone pairs, good grief, which would add more repulsion within the structure. I'll take it, but tough question that. I love this paper. What a great paper. There's my selected methyl group. Thank you, Pursuit. C15H24, boom. Electrophilic addition, boom. It's getting easier now. Mechanism, nice and straightforward. Yep, bum, bum, bum. Take all of those. 1, 2, 3, 4. They wanted the product too. Show your dipole, show your curly arrows, show the product, show the tertiary, intermediate. Love it. Next, forms a tertiary carbocation. Yep, and tertiaries are more stable than secondaries. Amazing. Next, nickel. Boom. Thanks so much. Hydrogenation. 150 degrees. That's what I'll say from now on. This, I loved the calculation. Thought this was amazing. Yeah, worked out the volume of hydrogen in meters cubed. They even did the same thing I did. Awesome. Love it. Giving it in meters cubed. And you can even switch it into DM if you'd wanted to. Love it. So you've got the 2 to the 6. That was the real challenge to that. Recognizing that the ratio is going to be 6. Most people wouldn't have done it. Yeah, just making you aware of it. That's a tricky question. That I hated this one. Biodegradation, decomposition, petrifraction, putrefaction. Gross. Decomposition. I'll take it. Biodegradation. Allow any indication of biological, yeah, because you can't do thermal. It has to be via organisms to produce methane and carbon dioxide. Climate change, global temperatures. See, there you go. That's why I don't do it. Global temperature increase, allow global warming, but climate change is there. Methane and CO2 are greenhouse gases. This was what an amazing question. I've got the wrong answer. Way! Okay, let's figure out why, folks. What did I do? 1 ton of landfill produces 12. I did something weird. So, calculate the annual volume. So from 1 ton produces 12 times 90,000. I did that. Have I got the right? No, I definitely haven't got the right number. I've got totally the wrong number. Where did I go wrong? Calculate the annual volume, calculate the moles of it, calculate. You can treat. No, hang on a minute. Assume the gas volume is measured. But they've given it to me approximately 12.5 dm cubed in the landfill per day. dm cubed. Why do I need to get to moles? They want me to. Oh, calculate. I've not read the question. Oh, beaten by 2. Beaten by 2. It says calculate the mass, not the volume. RTFQ, Mr. Duncan. Guys, I do not pretend to be perfect. Damn. That's the meters cubed. I'm not finished. So if that's in, let's convert dm cubed. Blimey. That's in meters cubed as well. I've not done myself any favors here. Let's see if I get the right answer. If I now do, let's turn this, that's meters cubed. Let's turn it into dm cubed by timesing it by 1,000, put it into dm cubed. Then divide that by 24 to give me it into moles, then times by 44. So 18,4,781 times 1,000 puts me into dm cubed. Divided by 24 puts me into moles. Multiplied by 44, and I get an enormous number in grams. Divide it by 1,000,000 to put it into tons. Count my zeros. I've got, if I do that, and then times by 44, the MR of CO2. Yeah, because this is going to give me moles, just to explain. Divided by 24 is going to give me moles of it. And then I'm going to do number of moles as grams over rams. The RAMs, of course, for CO2 is 44. So bring that over, times by 44 will give me that in grams, divided by a million to put it into tons. And I get, if I do all that, I get 338 tons. Oh, 339, rounds up, 9 tons. So RTFQ. Guys, it's so easily done. And that's the correct answer. Damn, I was halfway there. I'd get 1 maybe at best. Definitely lost some there, but not that it matters. And do you know what? I'm not going to give myself anything. Do it properly next time, Mr. Duncan. Suggest 2 advantages of incineration. Let me see if I can finish off the paper marking and then I'll move on. Full screen. 2 advantages. Okay, darn it. So decrease quantity, less space is needed. Love it. Incinerator can be used to generate electricity. Love it. Heat energy, generate electricity. No toxic gases. Answers. As resources are conserved, less energy lose. Allow produces less toxic or greenhouse gases. I lose the mark. Less. Easy fix. I'll add it in. Interesting question. Yeah. What a great set of information. Guys, all I can say to you is take your time, RTFQ it, read the full question. Yeah. Guys, it's been an absolute blast. I hope you have found it useful. I will leave you be for the rest of the afternoon. I'll put myself back on the screen momentarily. Let's just say hello. Guys, really fun paper. Really enjoyed it. I hope you guys find it useful. Have a nice rest of your day. I'll try and get another one done this afternoon if I can. Take care, guys. Bye.